heat exchanger analysis, and the log mean temperature difference. Okay, so if you're a chemical engineering student, you're going to have to get real familiar with sizing industrial equipment, right? Things like heat exchangers. To really understand how they perform, there are two core methods you need to know. First up, we've got the log mean temperature difference, or LMTD. This is your go-to method for simple exchangers, like parallel or counterflow. It basically calculates the average temperature difference that's driving all the heat transfer. You just plug this LMTD value straight into that fundamental equation, Q equals U times A times LMTD. But what about more complex setups like multipass shell and tube or crossflow exchangers? Well, that simple LMTD isn't quite right on its own. You have to adjust it using something called a correction factor, or F. So the equation just gets a little tweak, Q equals U AF times the LMTD. And you find that F factor on special charts that are based on your specific exchange's design. Finally, there's a whole other approach, the effectiveness NTU method. This one is super useful when you don't actually know the final fluid temperatures, because it helps you skip some really messy, repetitive calculations. Effectiveness is just a ratio. It's the actual heat you transferred divided by the absolute maximum possible heat you could have transferred. And that maximum is always limited by the fluid with the minimum heat capacity rate. So whether you're using LMTD's driving force or NTU's efficiency, these are the tools for designing and predicting heat exchanger performance. Let's dive into more detail.
All right, let's demystify a core chemi concept you absolutely need to know, the LMTD method. So here's the big puzzle in heat exchanger design. How do you average something that's always changing? You've probably seen this equation, right? Heat transfer depends on delta T. But wait, that delta T is a moving target. As the hot and cold fluids move, their temps change, so the temperature difference isn't constant anywhere. A simple arithmetic average just won't cut it. To find the true mean, we're going to need some calculus.
Okay, here's our game plan. We'll start with the problem and then build our way to a real-world solution.
To find that true average temperature, we're going to zoom in on one tiny slice of the exchanger. For just this slice, this tells us how much heat, dQ, moves across that tiny area, dA. And from an energy balance, we know the heat lost by the hot side is gained by the cold side.
Now here's the really cool part. We combine these to isolate the change in our temperature difference, d delta T.
This relationship is the key to everything. Now let's just integrate it over the whole exchanger.
Integration basically just adds up all those tiny slices to give us the big picture for the total area.
One last algebraic step, and we can bring it all back to the total heat transfer rate, little q.
And voila! All that work leads here. This whole expression is our true average, the LMTD.
So just think, it's the difference of the differences divided by the natural log of their ratio.
Okay, but that was for a simple case. What about more complex exchangers, like shell and tube designs? Easy. We just add a correction factor, F. This adapts our ideal LMTD for the real world.
You'll use charts to find F. Just calculate two simple ratios, P and R, from your system's temperatures.
But a quick heads up. For this method to work, you have to assume these two things are constant.
So, with the LMTD, you can finally do real design work, like calculating the exact area you need.
And look, a less ideal design with a lower F means you need a much larger area. Makes sense, right?
So the LMTD method is your best friend when you know all 4 inlet and outlet temperatures.
But LMTD isn't the whole story. It's a huge piece of the puzzle, but it does have one big catch.
What if you don't know the outlet temps? Trying to use LMTD becomes a huge iterative headache.
And that's where another amazing tool comes in, the effectiveness NTU method. But that's a story for next time.